of the string pheno part is going to be by Marcus, who is going to tell us about quantum Orientifold effective actions.
Thank you very much, Joe, and thank you to the organizers for organizing the program. It seems like a very nice program. I might have scared some people away with my title. It's based on some recent work by myself, Michael Hack, who's in the audience, and Jino Kang, who's at Kim Il-sung University in North Korea. It's based on this paper and also upcoming work that was really not out yet, so it's a typo.
How do you collaborate with that
guy? Yeah, that's a separate story. So why do we care about these things? Why do we care about one loop effective actions in string theory when there's so many other things we don't understand even classically? Well, one thing is stabilization. If we calculate the complete modular dependence of the effective action to one loop order, we can end up having either classical or quantum stabilization. And there are many aspects that this actually plays in ways you may not have imagined. For example, in KQLT, where you have a non-perturbative superpotential, these kind of calculations at one loop could actually impact how you do that stabilization and how that works out in detail, as I will try to explain later, even though that may seem confusing because, of course, this is non-perturbative, and I'm talking about perturbative corrections. Another way in which it could have importance for phenomenology would be also in the details of the soft supersymmetry breaking terms. There are many cases where you need to consider field space curvature of Kähler metrics, where you can't just canonically normalize your fields and just say, I don't care about corrections, but rather the corrections to Kähler metrics that you do have in minimally supersymmetric models could make a difference. And one example could be a large volume scenario, for example, that Joe and Fernando have contributed greatly to. So why do we care about Orientifold? So first, why do we care about quantum? Now, why do we care about these kinds of models at all? So some people, Orientifolds are very technical devices that may not seem to have a great relevance for example, for phenomenology. But of course, one reason we care about them is that supersymmetry is reduced. When you Orientifold type 2b, you get type 1, you break half the supersymmetry. So that's one attractive feature. To me, it's attractive that in compact models, Orientifolds give you consistency conditions. When you have Orientifold planes, you need to add d-branes. It tells you something about the number of d-branes you have to add. So to me, this is an attractive feature because it restricts your compactifications. To me, it's interesting that there's a wide variety of these kinds of models, that there are toroidal Orientifolds. They include toroidal orbifolds, Orientifolds over orbifolds. There's what Calabi-Yau Orientifolds, like in KQLT, and there's F-theory with Orientifold limits. So the arrow, of course, is pointing the wrong way here. The arrow should point there. Sorry. I just want to say that the kind of calculations that we do, that I will review here, are about toroidal models, minimally supersymmetric toroidal models, but we do claim that they have implications for other models in this range of models here. Of course, that's a highly non-trivial statement, and I will try to be somewhat clear about what I mean by that. So what are we correcting? What do we mean by correcting the effective action? Well, the classical general d equals 4, n equals 1 effective theory of gravity moduli and gauge fields looks something like this. You have a two-derivative term, you have Einstein-Hilbert, you have some moduli that generically at this point I will use capital Phi for open and closed string moduli, and later I will only use capital Phi for open string moduli. But here I just mean generically any moduli that have a Kähler metric in n equals 1, it's restricted to be Kähler. And you have some gauge fields, typically non-abelian gauge fields and some abelian gauge fields, and you have some coupling constants that have modular dependence. You have some potential for your moduli, which is we end up minimizing, and they have some corrections. So your first approach might be to say, well, I don't care about the corrections, I just worry about supergravity. I don't really care about string corrections, I don't care about alpha prime corrections or GS corrections, but I'm going to argue that you cannot always think like that, even if they look numerically small when you plug them into you plug in a certain point in modular space, because we actually want to know the effective action for all values of all classical values of the moduli to be able to actually stabilize them in the first place. So now I was asked to say a few words about how we do these calculations, in really backing down to the first step. So I'm aware that some of the people here in the audience are not working full-time on string perturbation theory. And in fact, this didn't come up very well. There are not that many people working full-time on string perturbation theory at all. There's a nice link from the archive website now. There are not many official links from the archive website to conglomerate websites, but this is one. It's called ceramics.org. How many have seen it? Nobody? It's at the top of the archive link website now. There's a link to this page. You can type in any phrase, 2 words only, and I type in string perturbation, and it searches full text, all papers from HepTH ever, and it immediately very quickly gives you a graph of the years and the number of times these words occurred, so you can see trends. And string perturbation theory started out at 3% of all articles in 90 when the archive started, and now it's down to 1%. So it's not a terribly popular thing to talk about, but I try to argue that it's of intrinsic interest rather than maybe it's terribly popular. You might say, well, the reason this went down is just because the general interest in string theory might have shrunk somewhat. But actually, that's not true as a relative statement, because string theory, if you just type in string, then you get about 50% or 60% of all papers in HepTH are about string. So string perturbation theory seems to be becoming a little bit of a lost art. And I'm going to argue that it's actually not just important for many things, but it's also a lot of fun.
I'm increased because Whiting is working on that.
Yes, and we're in good company. So string perturbation theory is 2 expansions. I'm going to be very basic in the next few slides just to get started for the people who haven't thought about this for a long time, perhaps. One expansion is the GS expansion in the worldsheet like this. So here I'm imagining computing a 4-point function, maybe gravitons, and expanding it in the G string. So for every factor of G string, you have a possibility of, you add a handle in closed string theory, and if you consider energies that are much smaller than the string scale, then you reduce to some kind of quantum field theory. So you have some kind of loop expansion in quantum field theory of the 4-point function here that descended from a 4-point function in string theory. And I would call these diagrams classical, semi-classical, and I would call these quantum. So anything that has a loop is a quantum correction to something, to an amplitude. Now, this is closed string. So this is the kind of picture you usually see perhaps in a basic talk about string theory. You might see these kind of diagrams. But what happens if you have a closed string propagating in a space where D branes are present? Then this kind of picture is modified a little bit because it happily propagates along, but then it can do something funny. So a closed string can break only on a D brane. Of course, if the D brane was space filling, then you would have this, you can break anywhere. But if you have a D brane localized somewhere, the string can only break, the closed string can only break on the D brane. And notice that I draw a charge and an anti-charge here. Of course, they can have to be totally neutral overall when they break like this. And so you can only have what's something called dipole charge strings. The string is overall neutral, but of course there's a dipole from separation of charge. And then of course this could equally well connect again. And you have a closed string propagating happily along. So just to repeat that, so what happened was that the closed string propagated along, attached to a D brane, and then kept propagating. So this is, you can think of this as in quantum field theory, you would have something like a wave function normalization or a mass correction or something you extract from a 2-point function of something propagating with some other kind of states present. So when you add these D branes, you add these charge states, and they can actually influence in loops or just in these kind of tree level diagrams the effective action. But I also want to argue that these kind of terms are already contained in effective actions that are very familiar, like the DBI action. It's one way to arrive at the DBI action is to compute terms like this and then extract the DBI from that. So that already has, for example, all the alpha prime corrections in it. So I'm going to argue that for my purposes, these kind of diagrams are not that interesting because most of it is known. I also want to mention that there are things about these kinds of tree level calculations that are not yet known, but they're not needed for exactly what I'm going to say. What is needed is another kind of process where you start with a closed string, propagates along, and then it splits twice in 2 different points. So I'm sorry that you can't see the D branes very well here. But this is one D brane, this is another D brane. So they split here, and the closed string also split here. And then, of course, this has to be overall neutral, this has to be overall neutral, but this can now be bifundamental. So it can be charged under this gauge group and charged under this gauge group. So it's a different kind of charge state that might appear now in this loop. And then, of course, it can reattach again. So this looks like a cylinder diagram. You have a closed string propagating. It attaches here, and then it exits here. And in the middle, it can have a pair creation of open strings, and this will descend to this in field theory. So you have a charge states coupling to the closed string, even though, of course, each coupling here has to be overall neutral because the closed string was overall neutral. So but this tells you that loop amplitudes really start probing the content of the theory more than the tree level diagrams do, in a certain sense. So I'm going to use simple models, as I said, for the extra dimensions. I'm going to use orbifolds and Orientifolds. An orbifold, of course, you get from identifying the spatial rotations. You have an action theta that takes a point here in space to a point here to a point here. And the identifier of them, you get a deficit angle, makes a cone with a conical singularity, this point here, which corresponds to this origin here. You make an Orientifold, which is a much more, in my mind, a more quantum operation. This is something completely classical. You just take a piece of paper and make a cone. The Orientifold, you need actually to think about how does the world sheet parity operation act on an oriented open string. Well, it flips the orientation. So that one becomes this one, but that means that this state, of course, is not invariant. So there's no sense that this is an eigenstate under this operator. But you can make an eigenstate by taking one of these, one on the right hand, one on the right pointing ones, and add one on the left pointing ones, and then you can pull out an omega out of that state, out of this one, and you can write it like this. So depending on the plus and minus, this have different eigenvalues under omega, but it is an eigenstate, unlike one of these oriented strings themselves. So you have unoriented eigenstates where you compute your traces, for example, and that's important to remember that here the states of the Orientifold are really superpositions of oriented states of different orientation. What kinds of models am I thinking about? So for example, typical n equals 1 Orientifolds would be T6 over Z6 prime just because there are two different Z6 actions people consider. And also you can think of T6 over Z2 times Z2. And these discrete groups act on the torus. If you have a T6 that splits into 3 2 tori, you have a theta action on each complex coordinate Z, Z1, Z2, Z3. That's specified by real components of this vector V1, V2, V3. So if I specify V1, V2, V3 equals 1, 6, and so on, I have specified how my action in this particular Orientifold acts on these coordinates, and then you get out of that some singularities, or you can actually get invariant tori. So for example, if you consider theta, just the action of theta itself, then all of these are twisted under theta. They all feel this twist with this particular twist vector. But if you look at theta squared, you see that this particular subtorus, if you square this becomes integer. So then this second 2 torus actually remains untouched. In that sense, this is only partially twisted. So there are sectors of the theory, subsectors, that in some sense preserve more supersymmetry. Sometimes they call it n equals 2 sectors. I will typically refer to them as partially twisted sectors. And the completely twisted sectors are the ones that feel all the action of the orbifold theta on all the 3 coordinates. This induces singularities. So for those of you who think it brings in singularities, you can have your pick. These kind of models contain both true Orientifold singularities, and they also contain pure orbifold singularities, and all put together in a nice package, which cancels tadpoles and is overall consistent. But of course, they're very simple models, and they may not suffice for kind of phenomenology you want to do. But they do have this variety. So the one loop effective action again is you want to know what the calorimetric is of the moduli. You want to know what the modular dependence is of the gauge coupling, and you want to know the potential. So I will give a quick review, maybe, I hope, not much more than 10, 15 minutes. But I want to give a solid review of what is known about this and what implications that has, and then I will want to come to our contributions, our recent contributions at the end. So the partially twisted strings give corrections to G and K. I will review that in turn. And then I will review the more difficult contributions due to the completely twisted strings, or the n equals 1 terms. I emphasize that the models we look at are usually minimally supersymmetric. So when you talk about n equals 2 sectors, that means that there are some sub-sectors that might appear to have more supersymmetry, but the models are always minimally supersymmetric. That's why I prefer these words that don't give people the wrong idea about the amount of supersymmetry. It's always n equals 1. The first look at corrections are corrections to the gauge kinetic function f, which is just the your real part of the gauge kinetic function is a holomorphic function of the moduli, and this gives you 1 over d squared. The physical gauge coupling, in turn, the one loop physical gauge coupling is given by some beta functions, some beta function running, and some threshold corrections due to massive states. So the reason I'm showing this slide is that you can say that I'm going to correct not directly the G and the K here, but I'm going to correct, ideally, if I preserve supersymmetry, I should correct F and the Kähler potential, then I have manifestly used supersymmetry in packaging my corrections efficiently by correcting this holomorphic function and by correcting this Kähler potential and not each single individual component. That's the ideal goal. So what do these kind of corrections look like? Well, this delta on the previous page, this threshold correction to the one loop gauge coupling, can have this kind of form. So you do the string calculation, you do this kind of diagram. We have two vectors here. You have a separation phi, and you have a field phi that parameterizes the distance of the 3 brane somewhere on this space-time torus with complex structure U, and a distance away from a 7 brane located at the origin. So this 7 brane would typically wrap the other 2 tori, as in the example I showed, but it would be point-like in this 2 torus, and that's where you have this distance phi. So you do this calculation, and you follow effectively very old work by Dixon, Kaplowski, and Louis from 91, and of course many other papers here. I don't mean to emphasize that these are the only 2 important papers, but of course there are too numerous to mention. I'm just mentioning our contribution in particular here, that you can think of this as a natural generalization of that, because in this paper, this was in heterotic, there was no sense of d-brane scalar. So they had an eta function here of u in their correction. In our correction, we have the d-brane scalar. We're effectively in type 1. We're in Orientifolds. And so we have this d-brane scalar, and then you have this theta function here instead of this eta function. But you can kind of already feel, if you're familiar with these kind of functions, that this will reduce to this in some suitable limit, because there's a limit in which the theta function reduces to an eta function. So you can see that this is sort of a natural generalization of this kind of correction that was computed in heterotic to the type 1 situation. Now this is, of course, a non-holomorphic contribution, because it's contribution to the physical gauge coupling on the previous page here. But again, you want to extract it's nicer to extract corrections to the holomorphic gauge kinetic function, and then you can actually extract this correction. This is not completely obvious. So you have this absolute value here, you have various things, but then I claim that you can extract this kind of correction as an addition, a holomorphic addition to the gauge kinetic function, using the elementary theorem that log absolute value squared is actually 1/2 real part of log z. So if you realize that the real part of log z, if you take the real part of this, you get the contribution to the physical gauge coupling, and then you can relate that to this term here. So I'm telling you that just computing this diagram, we get this kind of function, and then extracting that piece, we can think of a contribution to the gauge kinetic function. Yes?
There was a paper of Antoniades, Bacchus, and Judas, I think, doing this for type 1. What is the difference between yours and theirs?
Yes, so they did not have any continuous brane moduli. So theirs was okay. So good, thank you. So theirs was the natural generalization of Dixon, Kaplowski, Louis to type 1 without any scalars. So they also had these eta functions and theta functions with no first argument. So we added the first argument. Okay. But thank you. Please interrupt me if you have any questions. So these are corrections to F, and one sort of application of this, which is what I mentioned at the beginning, because this is kind of interesting, I think, that we usually think of non-perturbative superpotentials, for example, in KHLT type compactifications or related compactifications, that they're created by having, for example, gaugino condensation on some 7 branes. So then you want to have a 7 brane gauge kinetic function here, holomorphic, of course, in the superpotential. But then that gauge kinetic function receives one loop corrections, because it's holomorphic, usually it's protected from further corrections, but it does receive this one loop correction. So if you include this one loop correction on the previous page, you had a log in the correction. So the F1 loop had a log here. So we take e to the log, it goes down in front. So you can think of this calculation of the one loop correction to the gauge kinetic function as a correction of the modular dependence of this 4-factor A. So initially the 4-factor A is a constant, but now you think of this whole thing as a phi-dependent 4-factor, where this little a here is proportional to 1 over the number of the 7 branes. And it was actually pointed out already by Ganor already in 96 that you expect when the D3 brane hits the 7 brane, you expect that this superpotential should vanish. And this does vanish because theta function has a 0 at 0. So this is one way in which you see this work for you. Now, there's one important thing here, which is that these are string loop corrections, but without those string loop corrections, the non-perturbative superpotential doesn't depend on the 3 brane scalar at all. So they're not negligible corrections in any real sense. In other words, they make an enormous change in the superpotential by, for example, allowing it to vanish at a certain point in moduli space. So it's not a small correction to the original superpotential.
Question?
Yes.
So A generally depends on the complex structure moduli.
Sorry.
The
A.
grid vector capital A.
Yeah. This
So-
depends on the complex structure moduli.
Capital
Yeah,
A.
but that's in terms of the thetas, right?
Yeah.
But so is that known in Torn or Orientifolds? Can one calculate the grid vector exactly, or is it just an effective parameter as it is usually taken when we do modulus?
This calculation is just a calculation of starting. If you had a constant A to start with, then you have this addition here. Yeah. Or maybe somebody has something to add to that.
But at least you know that the full complex structure modular dependence is
absorbed.
is captured by theta 1.
Yeah.
Is there a distinction between like what's in the exponent and what's in the prefactor, or is that just a meaningless question?
I think at some level it's probably meaningless because, well, you can put a log, or I mean, I could have kept it in the exponent with a log, or I could have pulled it down. I think those should be the same functions. So I don't think so. But I think there's one important point here, which is that A is fractional. So you also see that there's a monodromy structure. If you look at small phi, for example, if you go around the 3 brane circles to the 7 brane, you see that there's a fractional power. So that is more explicit when you pull it down in front, that particular effect. And that is also predicted by, for example.
And the argument for they're saying that for phi equal to 0 is 0.
Yeah.
So that means you will have taken just the tree level f. You will get something that doesn't appear on phi at all.
Yes.
And somehow the phi dependence that comes after the one loop cancels that. And
Yes.
gives you something that it's very interesting. Right?
Yes, it's very strange, and it might make you very worried because you say, and again, I'm trying to emphasize this, that you think of loop corrections as being something small, and if it has a huge effect, then you think of it as being inconsistent. But here we claim it's not inconsistent. We claim that you have to include this correction in this sense if you want to talk about moving these branes. And this is the first, it's more like having, it's not like having 1 plus epsilon, and epsilon therefore has to be small if it makes sense. It's more like having 0 plus epsilon. If you talk about the potential, if you compute the potential for the 3 branes using the superpotential, of course you get 0 initially, and they get non-zero after that.
Right, but F3 level depends on other fields, I guess.
Well, F3 level is just
Modulus.
it's just T, for example.
Exactly.
Yeah.
So you're also modifying that T dependent because then you say that there will be no e to the minus AT by itself. It always has to come with a phi factor. So without the one loop, you will say, oh, it's e to the minus AT.
Yeah, without one loop, it would just be AT.
Sorry?
Yeah, without one loop, it would just be T
E to the
here.
minus AT.
Yeah.
Right. And then you add the one loop, and then
Yes.
you have e to the minus AT times some factor of phi.
Uh-huh.
So that means that you would have thought that for phi equal to 0 is e to the minus AT, and you're telling now for phi equal to 0 is 0.
Mhm.
That's what you're saying.
Yeah.
So essentially, the one loop is actually playing a role, canceling the tree-level dependence that is relevant for T.
If you will, yes. But one should say immediately that there can be also contributions of new states when you get to exactly 0. So you should rather think of this as being valid for not being exactly on top of the rather it shows you the dependence as you approach the 7 brane. But it's still true that this can become big compared to that. You can also think that the T in the Einstein frame also contains a GS factor. So this already has. So you can either think of keeping T fixed, or you can think of keeping T equals GS times T0. You can keep T0 fixed. So it depends a little bit where you keep fixed. But the way people usually do it is just to keep. If you just think of T here, which is the Einstein frame size of the. I mean, the real part is the Einstein frame size of the force cycle that the 7 brane wraps. Then you think of usually that's something you just give a number to. Right? You don't think of that itself as depending on GS. and then this happens what I said. You could think of sort of extracting a factor of GS, and then this would be a suppressed correction in that case. But in the way people usually think about it, this is not a suppressed correction. I'd be happy to discuss that in more detail. I'm sorry if it was not completely clear. My argument here was simply that I think these contributions are important, and people have in fact claimed that they're important in very detailed phenomenological situations, like because this then it induces new modular dependence, it induces additional dependence on the D3-brane scalars in, for example, D3-brane inflationary cosmology. So there's a paper by Baumann, Demarsky, Kleberon, Malacena, McAllister, Mergen in 2006, where they used our kind of arguments, and they then extended them to saying, well, this is not really, on some level, this is a supergravity communication between these two branes. So they were able to take this kind of argument and then sum over propagators in supergravity to get some kind of also modular dependent correction to the non-perturbative superpotential, and they use that in, for example, the Kleberon-Strasser background. So, and they claim that this is relevant for cosmology. There's also another sense in which this could be relevant, which is that we had a paper in 2010 where we argued that analogous contributions to this particular string effect could also impact sequestering, one of the strategies to deal with the flavor problem of gravity-mediated supersymmetry breaking. So this is just work in progress. We can't really prove at the moment that, well, we haven't yet finished this paper at the moment, but it looks like also there you get some contributions that could be interesting for phenomenology and cause, if you will, problems for sequestering. And this is the same kind of calculation that this diagram represents. So I was going to move on to Kähler metric corrections. This is something we did in 2005. We computed Kähler metric corrections to, again, partially twisted strings, I emphasize, to, for example, the Kähler moduli. So now you have the diagram I drew in the beginning of the talk. We have a closed string that propagates, and it can split into open strings, pair-create open strings, so they annihilate again. And that affects so that contributes to the two-point function of the closed string field. And you have in Orientifolds, you have Mobius strip diagrams and Klein bottle diagrams, and we use a certain kind of vertex operators that this just means what we do is really we rewrite, even originally in the string calculation, we try to write our variables in the most useful form for extracting corrections to the effective action of supergravity. And what I mean by that, I think will be clear in a little bit. I just want to say that I think it's a shame people don't name diagrams enough in string perturbation theory. In field theory, you always have these seagull names, you have these nice names for diagrams. So I proposed the TIE fighter diagram. If you notice, the topology is exactly like a TIE fighter. There's a brain here, and there's two insertions. So you compute in these TIE fighter diagrams, you can integrate using these useful variables. So we say we first organize our field, our fluctuations, our vertex operators in the most useful way to then be able to extract the not just the Kähler metric component, but also then integrate it to get the one loop correction Kähler potential. The potential that involves all the fields. In this particular Orientifold, it starts looking like this. So this is these pieces here are the tree level pieces. And then here is the one loop contribution. So we can put the explicit one loop contribution is suppressed by GS, and it involves this generalized non-homomorphic Eisenstein series. So this is this function, and this curly just means there are some over images of this function. But anyway, basically it's this function here, and we compute the coefficient. So these are some explicit string calculations that tell you what kind of dependence you should have on these moduli, and it also tells you the scaling with the Kähler modulus, for example, which can be important in applications. And then the logic here is usually then if you want to then apply this in, for example, large volume scenario or KTLT or something, you can't really trust any of the details here. You can't trust this particular form of the Eisenstein series, for example, but you can try to argue about the scaling with the moduli and try to generalize this to more interesting backgrounds. So I think doing this kind of calculation, you may not be so interested in the details. I am personally, but not everybody here may be. But I think you can learn something from them. Instead, I think the alternative is to say, well, we don't know anything about these, so we're going to ignore them. We're going to say they're not there. I think that's a worse approach. I think it's worse to say, we don't know these corrections, so we're going to set them to 0. I think a better approach is to take some simple model, compute them, and then try to extract some information for the model you're actually interested in.
So, Marcus, can I just
yes.
ask the previous question? Okay, so there's things inside the log. So there's a 1 over t plus t bar and one term. And there's a 1 over s plus s bar times t plus t bar in the other term. So like normally, so the factors of the dilaton, I'm just trying to see, because do these have different factors of the string?
Yeah.
These two terms?
This is suppressed.
by a factor of the dilaton, the extra factor of the
Yes.
dilaton. Is there a way of understanding? Like, so naively you could say if you're doing a one-loop calculation, you'd expect it to come in at order G string or something. You know, you would get a correction of order, like with one single factor. So the thing I'm not understanding is both terms seem to have like different powers of the dilaton.
Mm-hmm.
And naively, yeah, with the one-loop calculation, you might expect them all to come in at the same power of the dilaton.
Mm-hmm. It might be easier to think if you expand the logarithm, then you could just close the logarithm here, but then you get this divided by that. I don't know. So you should really think of this as a GS suppressed correction, but of course this is also in. Does that make sense?
Oh, I hear. So the first, you're saying that the first term in that the t plus t bar u plus u bar one is the kind of tree level D3 brane metric. And the next, yeah, sorry, okay, I understand. So that's the tree level one, and the next one is the
yes.
question. Okay, so yeah.
Yes, thank you for that clarification. So just to summarize, there's been a lot of work, well, not that many people actually, but there's been some work on computing modular-dependent gauge couplings. You would really want to know the dependence on what I call the generic moduli here, meaning all of these, so the axial dilaton, the Kähler moduli, the complex structure moduli, and the brane scalars, or brane moduli. You want to know the dependence on these to one-loop order, and I claim that for partially twisted strings, this is pretty much under control now for toroidal Orientifolds. What about completely twisted strings? I haven't said anything about those. Less is known. Are they not interesting? Well, if you ask Polchinski, at least if you look at his book, it says completely twisted strings effectively force the fields in the path integral to lie near some fixed points because they're twisted in every torus, so they're completely twisted. The path integral is therefore insensitive to the shape of the space-time torus, and so is independent of the untwisted moduli. If, on the other hand, they are only partially twisted, then the amplitude can depend on the moduli. So by this argument, everything I said until now does give you interesting modular dependence, and everything I say after now does not. Therefore, this is maybe not so interesting. But that's not generally true. So I'm going to say this statement is true on some level, but it ceases to be true when you, for example, add angles between branes, or if you add world volume flux, or things like that are interesting for phenomenology. And one simple way to think about that, which is not completely waterproof, but just to give you an idea, is that if you have an angle between branes, then the amplitudes would depend on the angles. So you have some angle appearing in some string calculation. And to define this angle in the first place, you need to say something about the complex structure modulus. The angle between the branes in space-time, even to say what that is, you need to somehow say something about the complex structure modulus. So this can depend on, for example, the complex structure modulus when you have angles. If you don't have angles, then you don't have that. So this was argued, for example, in this paper by Lüsten and Stieberg in 2003, where they computed these kind of diagrams. So gauge coupling corrections due to completely twisted strings or n equals 1 sectors. And you have this, some of you might have seen that in some of these models they have Kähler potentials at tree level that look like logs of gamma functions involving the angles. Some of you might have seen that at some point. Those come from these kind of formulas that you integrate some set of theta functions you get from your CFT contractions, and then you perform this integral and you get something that is a log of gamma functions that involves the angles. So this is a correction to the physical gauge coupling, so you can also think of it as a correction to the tree level Kähler metric. Either way, what I'm trying to say here is that these kind of corrections are more difficult. You need to compute more difficult integrals, and these people made some important progress in this paper by doing this kind of difficult integral. The good part is that you got other people helping you out. Riemann actually made a very similar computation in 1859 in his paper, that seminal work that started the field of analytic number theory. He computed a very similar integral when he tried to find Dirichlet series for a theta function type function. So it's good.
The archive number?
Sorry?
The archive number of the paper?
Yeah, fortunately he was ahead of his time.
Which paper has more citations?
That's a very interesting question. So, so I contributed something to this this kind of discussion in 2000 when with Pascal Berg, who was actually a postdoc in Cambridge, right here. The first time I was here, I was visiting him when there was still a construction site here. And in 2000, we wrote a paper where we tried to compute the calorimetric of d-brane scalars. So now we've changed the calculation. We're not having gauge fields here to compute a correction to the gauge kinetic function, but we compute a correction to the calorimetric of brane scalars by inserting brane scalars here. So now we should compute something correction to this. And they have these kind of amplitudes. So I'm not going through the details. I'm just trying to argue here that if you look at these integrals you have to compute here, they're generally tricky. So delta here is a real number, like imagine 0.1 or something. And they have the eta function here, and they have the theta function here. You have some combinations here, and you integrate both over vertex positions and over watershed moduli. So generally speaking, at this point, we could not, until recently, it was not known how to do this except to expand in this small parameter delta and integrate term by term. Then you can extract, for example, field theory anomalous dimensions, but you cannot perform the integrals. This means you have no explicit result for the one-loop calorimetric in the same level that we had in the partially twisted case, even without angles or flux. Here there are no angles, there's no flux. So this would just be constant contributions to the calorimetric that are maybe not so interesting for phenomenology, but that'll be the first step towards getting the modular dependent terms that you had with angles or flux, and not even that was feasible until recently. I think in the interest of time I will skip this. I just want to reveal that these calculations do give you something useful in that they are simple ways to compute anomalous dimensions that would otherwise in field theory be a horrible mess of coefficients. So this is at least an efficient way to do a calculation that you could also do in field theory. Now, what about string theory? So in this paper from December, we computed a S matrix where you compute, again, you integrate these brane scalar insertions over positions. You do some contractions here. There are only two vertex operators, so you just have this two-point correlator. It depends on the vertex positions, and it depends on the worldsheet modulus T, that you can think of, if you will, as the length of the cylinder, roughly speaking. And of course, these partition functions depend also on the worldsheet modulus. So they have to perform these integrals over vertex positions and these integrals over the worldsheet modulus and some over spin structures, because these correlators do depend on the spin structure. But again, we want to arrange the calculation in a way that is maximally useful for extracting something for the effective supergravity. And the way we do it in this paper, this is the same flavor kind of argument as we did in 2005 when we talked about these scalar adapted vertex operators. It just means arrange the vertex operators such that you can easily extract what is the correction to what in the effective action. And the way we do it here is we do type 2a, so we have angles, because it turns out fluxus is a little trickier, world volume fluxus is a little trickier, and it's not T-dual to angles in these non-trivial backgrounds. So we're going to focus on angles here. We're going to focus on type 2a with the 6 branes at angles for now. And then you define a capital phi, which is now specifically means Kähler modulus times brane scalar minus Wilson line. This is a Wilson line on the 6 brane, and this is the position of the 6 brane in the given 2 torus labeled by I. So I runs from 1 to 3. So you have these d-brane moduli that are composed of both positions and Wilson lines in type 2a. This is a little more complicated than type 2b. You just have composed in terms of something like just the complex position of the d-brane on the 2 torus, but here it's actually composed of both the position and the Wilson line. So you have a long brane, you have a vertex operator look like this with a Wilson line. So fluctuation of the gauge potential, and here you have a transverse fluctuation, transverse to brane, which is the position. And we label the directions, these directions by alpha and these directions by little a. But of course, what is along and transverse here depends on which brane you're looking at. And this was actually, there was some interesting technology for dealing with this kind of situation with completely arbitrary embeddings of branes and so on was developed by Fawad Hassan in Stockholm in 2003, although he wasn't in Stockholm at the time. You pick adapted coordinates. Actually, no, he wasn't in Stockholm. You pick adapted coordinates, so you adapt your coordinates to the brane and you work with adapted coordinates, and then you write explicit maps for embedding that in space-time and so on. And we were able to use some of his arguments to construct vertex operators. So our goal was to build vertex operators that look maximally simple, that look very convenient, and they look very familiar. But to do that in this slightly more complicated context, we have angles and so on, we had to do some adaptation again. And so one convenient metric, for example, is if you have a brane at angles, so you have a brane wrapped here. So this brane wraps twice around this cycle and once around this cycle. So you can draw the brane like this, but you can move this piece of the brane back here, And you see that these images have distance d, and the brane as a whole has length L, and it's convenient to use a metric where you have these distances explicitly built into the metric, so you don't hide any modular dependence in your periodicities, for example. So this is just to tell you that if you read this paper, we will tell you how to do this in the maximally simple way, so that you can write maximally simple vertex operators even in a slightly more complex situation that you might be used to. Another technique that we develop further is to say that when we work with method of images here, for example, for the world-sheet fermions, we always work on the covering torus of these spaces. So if we have a cylinder diagram, we extend it to an unphysical region here in the sense of method of images. So you might start with a covering torus that runs from 0 to pi here, 0 to 2 pi, and you identify under an involution that makes it two fixed lines, this and that. So this is now your cylinder, and this is still periodically identified. So this is one boundary in the cylinder, this is the other boundary in the cylinder, and that corresponds to this brane and this brane here. But now we extend it so we can also go into this unphysical region of the covering torus. And then it turns out that imposing the boundary condition you want for having branes at angles turns out to be equivalent to saying, instead of putting any boundary condition here, you use what's called the doubling trick. You introduce a holomorphic field that's valid everywhere on the covering torus, and it has then a holomorphic twist as you cross back into the physical region. So if you would move this point here along here, and you cross into this unphysical region, then all you have to do to impose a certain boundary condition with a certain angle is to say, what is the holomorphic twist as you cross over this covering torus? So this is simpler, at least for our purposes, than having explicit boundary conditions here that usually relate holomorphic and anti-holomorphic. So here we're able to only impose boundary conditions on the holomorphic doubled field. This is not terribly new in itself, but I think we package it together in a way that's easy to use. And it's quite different from what people did before. For example, Bertolini, Bilot, Lerda, Morales, and Russo, they did it quite differently when they had world-wide fluxes. They didn't do this. They had branch cuts in their vertex operators. And this is quite different from what we're doing technically, but of course the results should be the same. Now, physically speaking, what strength state can run in a loop in these models we have branes at angles? Well, the completely twisted states, as I've already said, are these states that feel completely the orbifold action in every torus, and they end up being localized at the intersections of brane images. So if you have a rotated brane, you have this brane here, then to make an orbifold invariant combination, you have to also add this brane and that brane. And you can also transport these back to the fundamental region here. So you transport this one back, you get this, this, and that. You transport this one back, you get this, this, and that, and that. And then you look where they intersect, and you see that actually it intersects here, 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 and at the origin, and that makes 7. You can in fact write nice and simple formula following these papers. You can write nice and simple formula that if you do this many times, and we wrote a little computer program that draws these pictures, you just have to map everything back to the fundamental region. So if you have more and more wrappings along one cycle, I just have a single wrapping along one cycle, but multiple wrappings on the other cycle, then you get more and more intersections, and it's given by the simple formula. So if you count intersections here, you see that you get these corresponding numbers here. So these actually appear as 4 factors in your amplitudes, because you have a localized state sitting at each point here, so you have copies of these these completely twisted string states sitting at these points, and they can all run in loops and contribute to the amplitudes. To actually do this in practice, you then have to integrate also the external states. So this you had to do also before, but this is a maybe slightly more detailed way to say it, that if we have an analyst diagram, again, I form it by involution of the covering torus. I act with involution on this, so I map this region to that region and identify. So then I get a fixed line here and a fixed line here, and those are the 2 boundaries of the cylinder. So we put our vertex operators along this boundary, for example, and then we fix one. You can think of, for example, fixing one here at the center of mass, and then you integrate the other one along this boundary. For the Mobius strip, you can make a Mobius strip again by the same evolution, where you tilt the original covering torus. That actually makes a Mobius strip. This actually also only has a single boundary, because this boundary here and this boundary here are the same, as you see if you write this, you draw this additional fundamental region up there. So that means you can just move this here, you can just perform this integral of the external state from here up to there. And these kind of techniques were actually developed by Cliff and others, though he may not recognize it in this form.
Previous life.
Yeah.
So Cliff's a string theorist.
Exactly. I think if you commit Mobius amplitude, that defines you as a string theorist for the rest of your life. Exactly. All right, so what do we actually get if we try to do these computations? we have to perform, as I said, these sums of spin structures of the partition functions and the correlators that depend on spin structure. And you get something like this. So this is actually a more compact way of writing the ugly-looking expression I had on the earlier slide. Just to point at it. This is the ugly-looking expression. And this actually comes from just a single exponential of a single bosonic propagator. You have from e to the ipxx. And then you have a fermionic correlator that you get from the super function of the worldsheet fermions here. So you just have the fermionic correlator, which is twisted, and you have an untwisted bosonic correlator where delta is p1.p2, where p1 and p2 are the incoming momenta. So this is the integrand. You want to integrate now over both position nu and modulus tau. And gamma is the overfold twist. So this is, again, this is here, this is without, sorry, I'm saying something confusing now. Yeah, so this, let me continue so I don't say something stupid. So we want to compute this general integrand here, and then we just want to integrate over nu and tau, but this is an external parameter, gamma. So gamma is a parameter that will end up in the original, in the final answer. And what I claim is that delta here acts most as a regulator, because this is in units of alpha prime. You ultimately want to take this to 0. And then you see that actually if you add and subtract this piece, so all I did here, I took the original expression and added and subtracted this piece, then it turns out that you can argue that this is actually odd. So the poles at 0 and 1 in these coordinates, so the poles at the two sides of the boundary cancel each other. So that means that this actually didn't contribute in the first place, so that means I can just look at that. And the important point now is that this was the only singularity you had here. So this has a single pole at nu equals 0, and that's subtracted here, so this thing is actually finite. And once it's finite, you can remove this delta. So there's a couple of technical steps here you have to do to argue that actually this amplitude is actually finite when you perform the integral. And once you've argued that, you can remove this regulator delta, and then you can do similar calculation for the Mobius strip, though it's not obvious at all that it should work the same, but actually works exactly like this. And then you can show UV finiteness in much the same way as you do in textbook calculations. So you have a 2-point function now, not a vacuum amplitude. And the 2-point function of the annulus and the Mobius strip, you can factor in the UV as having this 2-point function of the disk, plus these without insertions. And of course, if you have tadpole cancellation, then these vanish. So you see that it's important, even at the level of individual calculation here, that if you don't have tadpole cancellation, you have divergences everywhere. So divergences cancel in these diagrams because we have assumed tadpole cancellation. But then the finite part, once I've argued, although it may have been slightly hard to follow, but although I argued here that the amplitude is finite, then we compute the finite part, and it's 0. And there's a detailed argument why that is so in the paper, where we write explicit representations of these functions, and we perform integrals, and we show that it vanishes. But you can simply understand it by this rough argument, which says if we don't care about what happens at the poles, because I just said that they don't contribute, we can then extend the 0-1 integral, the integral we had from 0 to 1 of these vertex operators, to the entire contour. So now we make a formal extension of this integral to this entire contour, and we say that 0 is the integral of this function over this contour because there's no pole in the interior. And of course, then we can split this up into the 4 pieces, and this piece cancels that piece. So all you have left is this piece and that piece. And this piece is twisted. So you have a twist in this direction, then you get a twist when you move it back here. So you have a twist appear here. And then you have this integral that you actually care about. So you see the integral you actually wanted to know the answer to is equal to 0. Notice also that this assumes that b is not equal to 0. If there was no twist in this direction, this 4 factor would be 0, and then we give you no information from this argument. So it's actually sometimes the twisted calculations are sometimes simpler than the untwisted calculations because they have these non-vanishing features of this 4 factor element. The integral itself then vanishes. So very simple to summarize this calculation, answer is 0.
Why?
Yes.
This is argument. Yeah?
So let me come back to that in a little bit. So, well, the short answer is we don't really know why. And let me emphasize again, thank you for bringing that. Let me emphasize again, it is not guaranteed at all that these should be 0. And we then go on to compute somewhat related contributions that are not 0 in the next paper. So there's no general reason that this should be 0. In particular, supersymmetry doesn't help you because these are n equals 1 contributions. In n equals 2 sector, sometimes you can have vanishing arguments just from supersymmetry. But here, it's like this. In minimal supersymmetry, there just is no non-renormalization theorem for the Kähler metric. There just isn't one. I mean, there's nothing that guarantees that this shouldn't be renormalized. So it's more something about the individual details of these kind of amplitudes that this particular contribution vanishes. But I want to come back to that in a little bit. I just want to say also quickly review what is the other calculation we're working on where it doesn't vanish as far as we know. Here we try to do closed strings. Now I'm back to TIE fighter diagrams instead of having boundary insertions. This is the other calculation. We have TIE fighter diagrams. And we didn't put angles here yet because it was too hard for us at this point. Again, this is a mistake. It should be 12. So we try to compute these kind of diagrams. Let me just focus on one of them. Then you get a much uglier expression that involves this involution I've been talking about. Involution acts, if you have a 0 to 1 torus, then the involution acts as 1 minus the position bar. And that gives you so sigma is one of the surfaces on the previous slide. So sigma could be annulus, Mobius strip, or a Klein bottle. And they each have their involution, but we can write the generic contribution for all these three amplitudes. We can write like this, where again GF is the fermionic roll volume propagator, and GB is the bosonic roll volume propagator. And now I just give you a quick list of the recipe of computing these amplitudes, because I do think that we add something in terms of not just the results, but also in terms of the techniques. I think we helped develop some of the techniques here that I think can be of interest in many other kind of calculations. So you perform the spin structure sum, and then you lift this amplitude to the covering torus. So there's something called you can lift this if you have a function of the position W, and you happen to have another contribution which depends on the involution, which was used to create this surface in the first place, and you integrate over the fundamental domain of this surface. You can actually lift this combination then to an integral over the covering torus. So this means that this kind of amplitude, we hope to be able to reduce each individual contribution to just a torus calculation that is a very specific torus calculation. So now we have a torus integral we have to perform over the torus fundamental domain. We use zeta function regularization. We have this kind of integral where we have a fermionic propagator twisted, and we have a derivative of fermionic propagator twisted bar, and then we have to integrate that over the torus. And we claim that this kind of integral that used to be difficult for us is now not difficult. And we get something like, with zeta function regularization, we put an S here that we want to take to a limit later. Then we say the previous integral on the previous slide is this kind of double sum, and this happens to be the Epstein zeta function. And then you use the reflection formula, so you regularize by putting in this S, and then you use the reflection formula just like you would for the Riemann zeta function itself, and then you take this limit that you were going to take. So that's zeta function regularization. In this case, we also in the draft, we also have 3 other ways of regularizing this amplitude. So we compute this amplitude in 4 different ways, and we find the same answer. And finally, we perform the integral over the Roche's modulus T, which ends up being something like this: integral T over the fermion propagator, where some twist here, and you get some simple result in terms of elementary functions, where this is the digamma function, the derivative of the digamma function. The digamma function itself is the logarithmic derivative of the Euler gamma function. So this is just some constant. So this is the answer for this kind of amplitude. So I'm going to summarize that. I'm going to say that what we computed were finite constant additions for the Kähler metric of the closed string moduli in this paper. These finite constants can interpret at a point in modulus space, as I said before, can be interpreted as anomalous dimensions in certain cases. But that's not really our motivation for doing this, to compute those constants. Our motivation is to go on and compute modular dependence also in these terms, to compute the additional modular dependence you get from performing these closed string calculations that add contributions, modular dependent contributions to the Kähler metric of closed string moduli. So you can view this paper as a step on the way to doing that. And as Joe pointed out, there's some kind of string non-renormalization theorem in the previous paper, which is actually somewhat analogous to a similar result in a paper by Anastasopoulos, Antoniadis, Benakli, Goodsell, and Vichy in 2011, where they also find that masses of adjoint scalars don't receive any loop corrections in this framework. So we had some interesting discussion with Mark Goodsell about this, and it could be that there's some clear argument why these corrections have vanished, but we don't currently understand that. I would say it's a fair statement. So I think this is something interesting, that there's not often, I want to emphasize, that one can prove some kind of normalization theorem that does not follow from supersymmetry, that is valid for any orbifold, and is model dependent in that sense. It doesn't depend if it's Z3 or Z6. We didn't use that in our calculation. So we make a fairly strong statement as far as these kind of statements go about this non-normalization of the calorimetric of D-brane moduli. I think maybe the most important contribution in these two papers will be that we consolidate many techniques, some of which were known in Herodotic, for example, but we developed them further for branes at angles and Orientifold. And currently, I would say that these two papers by themselves, this one and the previous one, currently have no directly known implication of phenomenology. And I think the most interesting calculation is the one we haven't done yet. But that's always the case, isn't it? So I just want to emphasize that after our paper, of course, there will be a large contribution to the number of papers on this topic. So thank you very much.
So, can you repeat what you said about the non-renormalization theorem and whether it's model dependent or not?
Yeah, so this is the theorem.
Yes.
And we didn't use anything about we didn't use which orbifold it was. It's valid for Z3 or Z6 prime or so on.
But it's nevertheless
and it's valid for any
valid for orbifolds.
And yes. It's everything is for orbifold, but it's not. A lot of these statements that people make about these kind of models are you assume some brane configuration, you assume some orbifold Z3, and then you make some statement. But here we're saying it doesn't matter the brane configuration as long as it cancels tadpoles, and it doesn't matter the orbifold.
And what about the Antoniadis et al. Paper?
Yeah, they computed masses. So that's the.
That's also for orbifolds.
Yes, all for orbifolds. Yes. And they could be computed masses. So it's a 0th order term in the momentum. And we have p squared. This is a p squared term, if you will. This is a momentum term.
So can you make some arguments about what happens when you blow up the orbifolds, orbifold singularity?
No, it'd be very interesting to do the same calculation with a blow-up mode, for example. I don't know what the answer is. But again, I shouldn't say this too strongly, but notice that maybe I want to clarify something, that this is vanishing at the level of the integrand. You do the integration and you get 0. So that means that what was I going to say? Is not vanishing because of the sum over orbifold sectors. There was a paper, for example, on topological masses by Antoniadis and Taylor, where they computed some masses, and they said these masses vanish in string perturbation theory without blowups. And they say we put a blow-up mode and we compute the amplitude, and then we get something non-vanishing. Then the vanishing was because you took the blow-up mode to 0. Here it doesn't happen because of the sum over sectors. It doesn't seem to be directly related to orbifold symmetry, if you will. So at least it's not in the same way. If it is related to that, it's not in the same way as in the Antoniadis-Taylor paper, where you can explicitly see that because of the orbifold symmetry, the sum over sectors makes this vanish. Here's each individual contribution vanishes. In that sense, it's a stronger result.
But this applies only for the n equals to 1 sectors.
Yes. That's why I emphasized.
But that means that so is.
Yeah. So it means that if you have a model that has only n equals 1 sector, for example, Z3, then it's really that. But if you have both, like in Z6 prime, that's why we like Z6 prime because it's more generic. You have n equals 2 sectors, you have n equals 1 sectors, you have D3 branes and D7 branes, for example, in type 2b. And then, then of course you do have contributions. And yes.
So if you have a kind of a fake model which doesn't cancel tadpoles,
Yes.
there is a contribution?
Well, everything is infinite, so then it's not completely clear to me how to do this calculation. It's actually very interesting if you look at the details. One way to see this is that you write a Q series for this thing. Instead of writing in terms of theta functions, you expand it in Q series. And then it has one term which doesn't depend on the position. And that, so the propagator is kind of, what I'm going to say now is a little imprecise, but just to give you an idea, the propagator is roughly speaking odd under reflection in the nu equals 1/2 line, which is the reason that this piece vanished. But it's not, this constant contribution is not odd. So it's like if you had an odd function like a sine, where you add a constant, it doesn't give you 0 when you integrate. But if you add a bunch of contributions and this constant vanishes, if you have typal cancellation, then it's like you actually have an odd function, it actually vanishes. So it's not so easy to see how you would not, it would be hard to maybe see this result if you didn't have typal cancellation.
So the reason, this is probably totally irrelevant, but I guess, so in non-supersymmetric theories, I mean, the kind of main example of number normalization theorems are with anomalies, where they tend to be kind of exact at one loop. And so this is just, and then often in kind of string models, n equals 1 sectors are associated to anomalies in some, so things like branes at singularities, the kind of the n equals 1 tadpoles in some level are basically the same as the non-abelian gauge anomalies. So, I mean, this is just talking about, I was wondering whether there might be some, given this seems to be a non-normalization result, and you say n equals 1 theories don't have non-normalization, but the one place they do have non-normalization, which holds in non-super models as well, are kind of anomalies.
Yes.
Gauge anomalies. And so I was wondering whether there might be some, and this is just talking about whether there might be some connection.
Right.
That result too.
I think there could be a connection, which is what Mark was effectively talking about. He was saying something along those lines, I believe. He was saying that you can look at charge of different fields, and you can say that, well, only for certain combinations of charges, of course, you have anomaly cancellation. And then, in fact, in these old calculations of anomalous dimensions in string theory, you have two different contributions to anomalous dimensions. You have these kind of gauge loops, and you have fermion loops, or component fermion. So you have contributions due to the superpotential. You have a trilinear superpotential. You have contributions due to the gauge bosons. You can argue that if you try to come up with the argument why you can only have certain combinations of charges, it could be that you come up with combinations that make this vanish. And that would be required for this to vanish. So, but it's highly non-trivial for us. We have not been able to come up with an argument of charge restrictions to selection rules, basically. We have not been able to use selection rules to say whether there should be 0. In fact, the current arguments show that they should maybe not be 0 then. So it seems like there's something more going on, but my feeling is that probably one could try to construct an argument like that. But I really don't know at the moment.
One final question. Tell us about the North Korean.
About the what?
The North Korean. Your collaborator. How did you get to collaborate with the North Korean? How did you get out?
Well, the simple answer is that he was a student of Mokano in Munich.
Oh. And he was allowed to come out? And
Yeah, they come in pairs. They only pair produce.
But he's gone back since.
Sorry?
He's gone back since.
Yeah, he's back at Kim Il-sung now.
So do you interact by email, or how do you?
yeah.
Maybe we can take this discussion off record.
No.
I don't know if somebody's listening from Kim Il-sung University.
Yes, good idea. What is the next calculation that you say is the most important one?
The same calculation, but with angles or fluxes. So I want to compute this with divergent angles with fluxes, because then it will be modular dependent, as I just said. So then so that means that this is an additional contribution to our previous calculations that it's just unknown and people just ignore it. If you have angles and fluxes. If you don't have to care. So I'm claiming that there could be more modular dependent contributions that are simply unknown in models that have completely twisted strings. People have assumed, effectively because of this argument of Bolchevsky and others, that they just don't matter, which simply isn't true with branes and angles or fluxes.
And so branes and angles are dual to branes with fluxes, so that could be also.
Right, they're not. That's the kind of trick. So they're not actually T-dual in this framework because of non-trivial background. So you cannot actually, for example, you cannot say that the branes with fluxes in type 2b corresponding non-normalization theorem exists because ours does. So we cannot say that it vanishes in type 2b with fluxes. And in fact, with my current level of understanding, I would guess it doesn't vanish. Yes, so they're not T-dual. But you just have to redo it's not maybe that much harder, but you have to redo the calculation.
But in that case, you will still claim that the Polchinski argument will not apply.
Yes. Well, yeah, I think so. But